Okay, so sort of like that is going to be the following thing. We got a tire manufacturer. And here I'm recording this, I can't even spell manufacturer, so you just scribble. A tire manufacturer makes a tire that has a mean tire life of 50,000 miles. And in fact, those of you who have a car and have bought tires right on it say what their tire life is. So does this make sense? If they were to make those tires incredibly precise and take their time and get these machines that made them just almost exactly the same, you would get a whole bunch of tires which would be really close to exactly the same. Yep. And if they made them a little faster, some process that wasn't quite as exact. Now, think back to the chocolate chip cookie. It would still be good chocolate chip cookies, but not quite exact. You with me? So not all the tires are going to last this. And every tire will have on this 50,000 miles, it'll say under normal driving conditions. If you're driving four-wheel driving in the mountains all the time, or you drive all sorts of craziness all the time, it'll be down, but this will be normal. I was going to say this. It has a standard deviation of 4,000 miles. Because tires are tires. Some will last a little more, some will last a little less. So these numbers would have got by thousands of observations. That's how they would have got these, by thousands of observations, that the mean was this. And the standard deviation, some are going to last more, some are going to last less. If you would draw the following, and this is what we're going to be doing the whole time. This is called the standard curve, or the normal curve, or the bell curve. And if you draw a dotted line right down the middle, and write X bar, write the mean there. Here is the basic idea. The higher the graph goes, the more tires that would be in this example. Are there going to be a lot of tires that last pretty close to 50,000 miles, like maybe 51,000 or 40? Will there be a lot of them? Will there probably be way fewer tires that last 60,000 miles, or way fewer that wear out at 40,000? Right? Most of the tires will be right around the middle. So if you'd please leave a little room and draw a dotted line here, and if you would put 34% in here and 34% in here. Those 34% will not change. They will not change. The numbers eventually we put in the bottom, eventually those numbers will change every problem. Under this first dashed line, would you write X bar plus that little letter sigma, the standard deviation? And on the next one, would you write X bar minus the standard deviation? Would you draw another and another? And would you put 13.5% here and 13.5% here? The 34s, the 13.5s won't change. The numbers we eventually put on the bottom will change. And underneath this, put please X plus 2 standard deviations, and here X minus 2 standard deviations. And assuming I did my math correct, we're going to have 2.5% way out here and 2.5% way out here. Meaning in basic terms, only 2.5% of these are going to last a long time, and only 2.5% are going to last much less of a time. If you go to the internet, you will find different numbers here slightly. This can be more precise. Some will have 34.1% and will have 13.4%. We'll just use these numbers here. These are precise enough. These are precise enough. Cool. All right. I would like you to keep this one untouched and draw another one. And I'm going to just put down my numbers here so I don't forget. And we'd like you to draw another one. Oh, wow. We got some fun today. Hi, Whitney. Hi, how are you? Would somebody take the mail? Thank you very much, Whitney. I like the bow in your hair. Everyone say, have a great weekend, Whitney. Have a great weekend. All right, see you, Whit. Bye now. Bye-bye. See you later. All right, very awesome. All right, would you please, on this problem, put 50,000? That is our mean average. That's how much we figured out. And that came from the original problem that I just erased those numbers. The 34% stays, and we are going to add 50,000 plus 1 standard deviation, and please put 54,000. Okay, I'm going to start with a super basic question. What percent of the tires will last between 50 and 54,000? 34%. All right. Subtract 1, so this will be 46,000. The 34% will stay right in there. The 34% will stay right in there. Cool. We'll go to another. And this becomes 58,000. And this will go 42,000. Our 13.5% stay the same. And our 2.5% stay the same. So this tire company says we're going to replace all the tires that fail before 42,000 miles. Will they have to replace 2.5% of the tires? Okay. Then what the company is going to have to do, is make sure that that is acceptable to them. And maybe they'll say that is way too many tires we have to replace. So what the company might then choose to do is buy new updated tire making equipment that makes the tires more exactly the same. Boy, that's bad wording. More exactly the same. So maybe what they're going to do then, they buy new equipment that has laser tire making. I don't know how to make tires. They still have a mean of 50,000. But then their standard deviation is going to go down to 2,000 because the tires are more and more like each other. Does that make some sense? Okay, that makes some sense. Cool. So then, in that case, we got 50,000, and now this would be 48,000 and 46,000, and once you get way out here, 44,000. And 42,000, you could actually figure out this percent. We're not going to, but I mean, it's just a tiny, tiny decimal. So if they would make the tires, and they have to decide, is it worth it to buy these new machines that are super perfect? All right, I have to stop this every 11 minutes. Okay. No, every 15 minutes. All right, I'm going to tell you a true story, and I shouldn't record what I'm about to say, but I'm going to tell you. Okay. So I live in South St. Paul, and I'm not a super math geek, but I know how many songs I can listen to as I'm coming here. And my time to drive to work, for real, averages 11 and a half minutes. It averages 11 and a half minutes. Because I do look at how long the songs are, and because I did this a few times just so I would have this for class. The standard deviation is 3/4 of a minute. So here's the deal. I live in South St. Paul. I come out, I have a stop sign. There's never anyone at the stop sign, so I go on through. Even if there's I go on through, I shouldn't record this. This is bad role model. I'll mute this. The last time an officer pulled me over for not stopping well at a stop sign, came up and said, "Sir, you didn't even try." I said, "Yeah, you're sort of right." So he said, "Try harder." Okay, all right. And then I come down a hill, and there's a stoplight. And it's a pretty good stoplight. I rarely have to stay more than a minute. It's usually less than a minute. And then I get on the freeway from South St. Paul. I exit at Lake Road, so now I'm right by Super America Speedway. Can you shake your head, you know where I am? Okay, and then I come on Lake Road, and then I turn. Is it Courtly I turn on? There's that one stoplight right past Super America, and I come to Courtly. I don't have many stoplights that mess up my commute. They're usually pretty quick, so my time is actually pretty close to the same every time. It's pretty close to the same every time, and those are actually the right numbers. So if you would please start a standard deviation. Draw all the numbers for my scenario. I'm going to stop this recording and start a new one because I found I can only go 15